Hi, Algebra 1. In Lesson 2, we got started looking at some patterns, and in Lesson 3, we're going to continue this, and we're going to continue building quadratic functions from those patterns. Here we go. In the first row here, we're just looking at what would the area of each of these be if the side length of the square was 4. So our first one would be 4 times 4, which is 16. The next one would be 4 times 4 minus 1, because we're going to subtract that square in the middle there and get 15. And then figure C, I would have to take 16 plus 1 would be 33. So now we're looking at what if the side length is x, meaning we don't know what it is. So square or figure A, the area would be x times x, which we're going to write as x squared. We're going to get used to doing that. And figure B, if the side lengths were x, I would have x times x minus 1. Or in other words, x squared minus 1. That would be the area of that figure. And in figure C, we would have one square that is x squared. And then the area of the other square would also be x squared. And then we're going to add on that 1. So to combine like terms here, I would have 2x squared plus 1. In the next one, if the side length of the square was 4x, what would our areas be? So I'm just going to label these right now. And our first one, we'd have 4x times 4x. Well, that's going to be 16x squared. All of those terms are being multiplied. So you would just take 4 times 4, which is 16, and x times x would be x squared. The next one, well, I would have that 4x times 4x, but then I'm going to subtract 1. So I'm going to rewrite that as 16x squared minus 1. And then this last one, I would have a 16x squared in each of those squares. So I have 16x squared plus 16x squared plus 1. And to combine like terms, I would have 32x squared plus 1. And our last row, what if the lengths were x plus 3 for the square? Well, for our first one, we'd have x plus 3 times x plus 3 would be the area, but I would rewrite that as just x plus 3 squared, and we're going to leave it like that for now. Figure B, well, it would be that same area, x plus 3 squared, but then we'd have to subtract off that 1 for that little white square. And then figure C, remember each of these squares is going to be x plus 3 squared. So I have 2x plus 3 squareds. I'm simplifying here as we go. And then adding that one little square. So for all of these that have variables, we aren't able to come up with actual numbers, but we're able to come up with expressions that we could plug a number in for x and figure out the area of that figure. In this pattern, I'm noticing that I have a square in the middle that has the side length of my term. So this one was 3 by 3. And then each time I'm adding 4. So in step 5, I would see a big square that is full of squares that's a size of 5 by 5. And I'm not drawing all those little squares here because I'm just trying to get the idea of what is this going to look like. And then I know that I'm going to be adding on those 4 squares. Step 18, I'm going to have a big square in the middle. That's an 18 by 18 square. And then 4 squares being added on. So here I'm explaining and showing how I know that step 5 is going to have 29 squares and be 25 in the middle, and then adding 4. Step 18, I have a square in the middle, it's 18 by 18. So that's 324 squares, and then add those 4 to have a total of 328 squares. So my equation down here, I always have this big square in the middle, and that's going to be n squared. It's going to be my step number times itself, or n squared. And then I'm always adding on 4. So there's the expression that I could use to find the number of squares in any step number. When the question says to explain how each part of your equation relates to the pattern, this is one way you could do it. This n squared piece is showing us the big square in the middle, right here. And then plus 4 comes from adding 1 square on each corner of the pattern. That's right there. You could do this problem lots of different ways. I first set up using the expression in the equation, plugging in the step number for n, and figuring out how many squares do I need in each step. So that's the first thing I did. So step 1 has 0 squares because 1 squared minus 1 is 0. Step 2 is going to have 3 squares. Now I'm thinking of creating a square here with the n squared. So I really do have kind of an imaginary square happening here. That's 2 by 2. But then I have my missing square right there. That's the minus 1 part. Step 3, again, I have a big square here. That's 3 by 3. But then I'm missing 1 square there. That's the minus 1 part. Here's the next step in my pattern. I'm going to have 4 columns and 6 rows going on there. Number 2, Kieran says that the pattern is growing linearly, meaning is this a linear pattern? Are we adding the same thing each time? And in this case, no, we are not adding the same number of squares each time. And you can see that we started out with 3, now we have 8, now we have 15. Well, to get from here to here, we added 5 squares, and then we added 7 squares. So we're not adding the same thing each time. Looking at number 3 here, Diego and Jada saw this pattern in 2 different ways. Diego wrote the equation f of n equals n times n plus 2. So let's just see where he finds that pattern here. Looking at step 3, our step number is the number of columns we have going across, and then the number of rows we have going up and down is n plus 2. So to find the area, or find the number of total squares there, you could do n times n plus 2. Now Jada did it differently. She saw n squared plus 2n. And so n squared, I'm looking for a square, in this case 3 by 3, because that's our step number. So that square is n squared. And then we're adding on 2n, 2 rows of 3. So here's our n going across, that's the width, and we're always adding on 2 rows of that. Let's just double check that that works here. Here's our n squared, and then here's 2 rows of n width. So it's the same thing, and also if you use the distributive property, let's start with Diego's here, and I want you to draw this out, use the distributive property, n times n is n squared, and n times 2 is 2n. So this again is showing that they really are the same thing. The other thing to note here is that in Diego's equation, just because you don't see an n squared, it is still quadratic. And that's because if you do the distributive property, you end up seeing that n squared in there. So just keep in mind, if you don't see an n squared term, it could still be quadratic. Try out the distributive property and see if it shows up.